Hello, my name is Mark. I'm one of the staff engineers here at the UCSD Makerspace, and today we're going to start talking about CNC machining. So, what is CNC machining? CNC machining is known as a subtractive manufacturing technique, which means that you take a piece of material that is larger than your desired part, and then you use the CNC machine to cut away everything that isn't your part, leaving you your part. Now, this is very different than what you have probably used before, which is 3D printing, where you're starting with nothing and then depositing material where your part is supposed to be, and that's known as additive manufacturing. Now, CNC machines come in all kinds of different shapes and sizes, and you got mills and lathes, for example, and today we're going to go over a CNC router, which is a type of a CNC mill. These are 3-axis machines with X, Y, and Z movement. On the Z-axis, you have something called a spindle, which is what spins your cutting tools at various RPMs to do the actual cutting. Now, these machines are generally used for large format processes, so they have generous work envelopes, but still maintain good rigidity and precision. We use our Shapeoko CNC routers for a lot of training purposes, as they're easy to use, durable, and relatively robust, and they can work with material up to 23 by 18 inches. We even have the large CNC router, which will work with material up to 4 by 8 feet, as well as various other metal types of mills that are more rigid for cutting harder metals like steels. Now, for tooling that goes into these machines, the one you're most commonly familiar is probably known as a drill bit. You probably have used these in drill presses and hand drills. Drill bits are great for making holes, but however, they're only meant to make holes. They can only be used in up and down cutting motions, and to be absolutely frank, we don't often use them in our routers due to the limited Z travels a routers has, and the fact that you can also usually get away with just using an end mill. And with further ado, end mills are the bread and butter of machining. These are tools that can cut on the sides as well as the bottom face. Now, with end mills, you don't actually want to drill straight down with them. You generally use the CNC machine to make a helical move that bores into your part. Afterwards, the end mill can be pushed around and then used as a side cutting tool. Now, end mills comes in all kinds of different shapes, diameters, and lengths. The most common ones are probably these square tipped ones, where the end cutting flute is perpendicular to the sides. We generally have these in 2, 4, 6, and 8 millimeter cutting tools, and they're generally used for all kinds of different types of cutting. Now, the other most common type are known as ball end mills. These end mills have a half sphere tip and generally used for 3D surfacing and creating complicated geometrical shapes. Now, when you're designing your parts, you gotta think a little about how you're gonna design the part so that the machine can make it. Unlike a 3D printer, the CNC mill can only cut what the tool can fit in. So that means that when you design a pocket, it means that you have to have an end mill that is small enough to physically fit into the pocket to be able to cut it. You also have to have an end mill that is long enough to cut it. Most commonly, our end mills will only cut up to an inch deep. So if you need to cut a pocket deeper than that, you're going to have to get creative with the tool path or buy a larger tool. Now, you can usually solve most of these problems with money. Tools that are not of standard length or sizes get very expensive very quickly. Also, when you're cutting a pocket, you cannot have any sharp corners, as because the end mill is round, all of your corners at minimum will have a radius of the tool size. You also want to think about the rigidity of the tool, as there's a lot of cutting forces and part of the tool is cutting for different materials. Because everything moves under high load, you want to make sure you're using the shortest end mill for your cut, and then you also got to realize that the smaller end mills are much more likely to break. I've used end mills as small as 0.5 millimeter, and they snap if you look at them wrong. So for the most part, you want to make your part so that you can use a 6 millimeter or bigger end mill. We find those to be fairly durable. Anything smaller than that, you have to start being really careful with your fixturing and your tool pathing to make sure you don't break the smaller tools. And then as you're designing your parts, you also got to think about how you're going to fix your part, as you have to hold the part down somehow. There's a lot of different ways to do this, involving anything from double-sided tape to super glue, all the way up to custom fixturing, clamps, and everything in between. For the most part, on the mills, we use large industrial vices. In our routers, we use a combination of wood screws, clamps, glue, double-sided tape, or whatever else works. If you have a part that you're unsure about, feel free to talk to some of our Makerspace staff, and they'll do their best to guide you through your design process. Now let's talk about the software that we need to be able to do this. For the most part, you're going to need a 3D model. This can be designed in a large range of CAD software, which stands for computer-aided design, such as Fusion 360, SolidWorks, Onshape, Creo, and more. Now, the CAM software, which stands for computer-aided machining, it's a software that takes a 3D model and then converts it into a G-code file for you to use on the CNC mill. You've probably heard of slicing as for 3D printers. This is similar to that. However, this process is a lot more manual and requires a lot more input from you, the user. Some of the slicer software that we use in the shop include VCarve, which we often use for our routers and large format jobs. SOLIDWORKS HSM for SOLIDWORKS users, as it is a plugin that works natively with SOLIDWORKS. And then for most other applications, we recommend Fusion 360, as it is good general purpose CAM software and CAD software that runs on Windows and Macintosh computers. Today we're going to be talking about Fusion 360, as again it is probably one of the best general purpose softwares, and you can import files into Fusion 360 from all the other CAD softwares I talked about. So the main workflow of the CAM software involves: number one, setting up the XYZ coordinate system, which is going to be also known as our work coordinate system for the software and the machine to interpret. You're going to want to pick and choose what tools you're going to want to use to do your cuts. Then we're going to go through and select the operations, and then the geometry we're going to cut with those operations. And then we're going to use a post-processor to export the G-code to a flash drive to take over to our CNC machine. So let's get over to Fusion 360 and get started. Hi everyone, this is Mark again. So now we're going to go over our Fusion 360 CAM tutorial, and we're going to walk through how to make this part out of half-inch thick MDF or plywood today. This is going to be a complete tutorial, show you how to go from just a model to having your completed tool paths. Now the first thing we want to do is download the model in the link description, as well as download and install the tool library. We're only going to be using one tool, so it's a relatively small download. If you have any questions or have issues doing this, please ask one of our staff members and we'll be able to help you out. So this is going to be a really simple, really basic intro into CNC programming. You're going to be able to make this on any of our Shapeoko CNC routers, and this is going to give you the foundation to build up your skills in CNC machining. So let's go ahead and jump into Fusion and get to it. In Fusion, CAM is known as the manufacturing tab. So the first thing you want to do is click this left drop-down menu and go into manufacture. And this will bring up your CAM tools. Now, for Fusion CAM and most other CAM softwares, every face you want to machine has to be its own setup. So the first thing we're going to do is create a setup for the face we want to machine, which on this part is just going to be the top face, so we'll have only one setup. You're going to create your setup by clicking this folder icon, and it's going to bring up the setup menu. Now, for us, there are two main things we have to do in the setup menu, and that is set the work coordinate system that tells the machine where our X, Y, and Z zero is, and then also set up the stock so the machine knows how much material we have. So now the first thing we're going to want to do is go ahead and set up the stock. So we're going to click that, and we're going to go into Fix Size Box. And this allows us to measure our stock and tell Fusion how big the piece actually is. So that's what I'm going to do right now. So I'm going to actually go ahead and measure my stock with a pair of calipers. So we got 4.06 on the x-axis, and on the y-axis we got 3.22. Now, Fusion is telling us the model is 4 by 3 inches, so that means our stock size obviously has to be bigger. And when you cut your stock out on the bandsaw or chop saw, you always want to give yourself a little wiggle room. Now, for the z-axis, our model is ½ inch, because that's our nominal thickness, but the plywood I have is actually measuring 4.7 inches. And we're going to manually deal with this later on, but you still do want to know how thick the material is, so you make sure that you cut all the way through and you don't cut into the machine's table too much. After we set our stock size, we're going to go into setup, and now we can set our XYZ coordinate system, which is also known as our work coordinate system. By default, it looks like Fusion has put it in the middle. We're going to put it into this left corner by clicking this little white dot, so that's going to be easier for us to set up the machine with. And as you can see, we already have it in the right orientation. We got the x-axis going along the long edge, the y-axis going along the short edge, and the z-axis going up and down parallel to the features we want to cut. And that's key. And that's super important to make sure you do so, as Fusion will only let you cut into features that are parallel with the z-axis. Now, we also want to make sure we have the z-axis on the top of our part, which we do. That's going to make setting our tool zero really easy down the road, and overall that's going to be the easiest way to zero the part and our machine. Now, if you're doing something more complicated, you might want to put the origin on a different corner, or sometimes in the center of a feature. For something like this, where we're just cutting flat pieces of wood on our CNC router, you can pick almost any corner, and as long as you remember which corner you picked in the CAM software and do so on the machine, you'll be fine. After we do all of that, we're going to hit OK, and we're going to be ready to go. Now, to recap real quick, the setup is for setting the work coordinate system and the stock size. And when you set the stock size, you do want to actually use a pair of calipers and measure it. Okay, once we have set up our setup, we're now going to be able to create our operations to actually start cutting into our material. Now, in Fusion, we have 2D toolpaths and 3D toolpaths. Now, 2D toolpaths are generally considered 2.5D, and that means that it can cut parallel to the Z-axis using lines to drive the cutting toolpaths. So as you can see on our part is a complete 2.5D operation. We have different depths which we can control, but everything is a 2D. But everything we need to cut is simply a 2D sketch. Now, 3D toolpaths generally involve more complicated geometry, where you have more 3D surfacing or actually driving the toolpaths, such as trying to cut a sphere. Now, that's going to be a little out of scope of the video today, so we're not going to really talk about that, but we will show you some examples of 3D toolpaths on the screen right now. Now, one of the most powerful 2D toolpaths is known as 2D adaptive clearing. This is a smart toolpath that does its best to remove material as quickly and efficiently from your part on any type of machine. So that's where we're going to use to cut out these circles as well as this pocket right here. You can also do things like profile and 2D pocket, which are more manual toolpaths that will allow you to do the same thing, but you're going to have more steps and more setup required to do so. So to start off with a 2D adaptive, we're going to click the 2D button and select 2D adaptive clearing. And that's going to bring up our menu screen for selecting the toolpaths. Now, Fusion tries to make all of its menus look the same, so it is easy for you as the user to use them. So all of the toolpaths will have a very similar menu to what we're about to go through. Where the first page, you select a tool. The second page, you select a geometry. The third page, you select the heights. The fourth page, you select your cutting parameters, and so on. Now, we're going to see a lot of boxes and a lot of numbers while doing this. And some of these numbers are very important, where if you misplace a decimal point, you could crash the machine, break something, and scrap your part, while some of these other numbers in years of machining I've never touched. So until you fully understand which numbers do what, you want to be really careful that you have set everything up correctly. And if you're ever confused about a number, you can mouse over the field and a tooltip will come up that explains to you what that field does, and often we'll have a graphic to help you understand what that field is doing. Now again, if you're ever confused about anything, feel free to talk to a staff member and we'll do our best to help you out. So as I said earlier, the first page is selecting the tool. So we're going to hit select and we're going to go into our test project and you'll see we have a 6mm end mill already loaded up. And we're going to hit select. Now this is going to pull up a default feeds and speeds that I've already set. We're not going to get too in-depth into feeds and speeds, but there are two things I want to touch on. Number one, that is your surface feed. And number two, that is your chip load, or your feed per tooth. So, surface speed is the speed difference between the cutting tool and the surface of the workpiece it is operating on. And that is driven by the tool diameter as well as the RPM of the spindle speed. Now, different materials have different surface speeds. For wood routing, we're often in the thousands. And then we're going to be also limited by our machine and its maximum RPM and rigidity and so on. There's a lot of complicated math that you can use to calculate these numbers, as well as manufacturer guidelines when you buy tools and machine tools. Now, these are numbers that we personally have tested, so we know they work, and it's going to be a good starting point for you getting going with your part. So for surface speed, we see we have 1100 keyed in, which gives us a spindle speed of 18,000 RPMs with a 6mm tool. Now, feed per tooth is how big of a chip the tool is cutting. Now, this tool has two flutes, which means it has two cutting teeth. So for every revolution of the tool, it is taking 2 cuts. And we want each of those cuts to be around 1/1000th of an inch, which is why it's set to 0.001. And that gives us a cutting feed of 40 inches per minute. Like I said, this gets fairly complicated, but that is just a starting point for you to kind of understand what's going on here. So next, we're going to go on to our geometry tab. In this tab, we're going to be able to select what geometries you want to cut. So I'm going to select these 2 bores first, and I want to select the bottom contour of the bore. And you'll see why in a second. So I'm going to go ahead and do that. And we also want to select the bottom contour of this pocket. And then when you zoom in, you'll notice that each selection has a little red arrow. The red arrow dictates what side of the line you're going to be cutting on. So these are pockets. We want the arrow to be on the inside of all of these features. Which you can see here, that's all correct, so I'm going to be happy with that. Next, we have our Heights tab. The Heights tab controls where our tool starts at, ends at, and where it goes in between cuts. So the clearance height is where the tool will start and end at, and that's set to 0.6 inches by default. The retract height is set to 0.2 inches. That's how high the tool is going to retract to when it moves from one feature to the next. And the top is set to 0 inches, which is our Z0. So obviously you want the retract and the clearance height to be above the part, so I'm going to leave those as is. If you have screw heads or clamps that may be on the top surface of the part, you might have to increase those numbers to make sure your tool doesn't hit anything when it's traversing the part. Now for the top, that's going to be set to stock top, which is our Z0, which is fine. And our bottom height, as you can see here, is defaulted to selected contours. And that's why we selected the bottoms of the contours earlier, as that now Fusion will simply use our geometry to determine how deep to cut in all of our features. So that's going to work out real nicely for us. So next is our passes tab, and this sets our cutting parameters for the tool. So a couple of things we're going to pay attention with. We're going to start with the optimal load. The optimal load is how big of a cut the tool is going to take. We're going to change that to 0.1 inches, which is roughly half the diameter of our 6mm tool, and that's generally a pretty good starting point for a lot of wood cutting applications. Next, we can see here there's a stock to leave option. And we're going to actually uncheck that. Because if we leave this checked, it's going to leave this amount of material on all of our features, which we don't want in this case. Now, for some examples of why you might want to use this feature, if you're doing metal cutting, you generally want to leave a bit of material to then come back with a contour toolpath to do a finish pass, which will give you a better surface finish. Now, for wood cutting, I find that the finish pass isn't really necessary, as in you're not going to get a better surface finish if you do one, so we're not going to spend the time doing so. After that, we can go into our multi-axis, which simply tells the computer we have a 3-axis machine, which all of our routers are. And in the last tab, we have the linking parameters. Now, what this does is this does our leads in and lead out. When our tool starts cutting, we're going to use a helical spiral that's going to ramp into the material, and then we're going to then have a small arc to lead out of the material when we're done cutting. Now, these default numbers on my screen will work fine. You just want to double check on your screen. You have the same numbers as I, but for the most part, Fusion's default for this will work. We hit OK, and now the computer is going to generate our toolpath. As you can see, it just did, and it looks like everything is good to go. The yellow lines are our retract and move commands, where the tool is going to be wrapping around the part. The red lines are the helical bores that will enter our part, and then the blue lines are our cutting toolpaths. This green preview shows what the toolpath is going to be doing, so you can see that it cut 2 circles and my pocket out. I don't see any excess material removal, so that indicates that it looks like we've done everything correctly. So now you can see that our square corners are actually rounded over. Fusion tries to be smart and then cramps a tool into the corner as tight as it go, but you will still get a radius where you have sharp corners. You want to again double check on your screen, you see the same thing. If you see any gouges or any additional material being removed, you've probably done something wrong. You're going to want to go back and double check your work. After we've done our 2D adaptive, next thing we're going to do is a 2D contour around the outside of our part. Now it's going to bring our part to size as well as radius our corners. So for the 2D contour, we're going to go ahead and select 2D contour. Again, we're going to get our selection menu, which is going to look very similar to the 2D adaptive one. On the first tab, we got our tool. Now, Fusion is going to automatically load in the same tool that we used from our last operation with all of the same feet and speeds. So that all looks good. So we're going to just be able to go on. Next tab is going to be the geometry. And again, we're going to select the bottom of the outside contour. And again, you'll see this red arrow. Now, because we're cutting on the outside of this line, we again want to make sure the red arrow is on the outside of the line, which it is by default, so we're going to be able to move on. If your arrow does not show on the outside of the line, you're going to want to right-click the chain and hit Edit, and then go over here and select Reverse. But I'm not going to need to do that, so I'm not going to do that right now. Next, we're going to go back to our Heights tab. You can see we have the same clearance and retract height, which are above our part. We also have a feed height, which is where the tool is going to start ramping into our part, and by default it is set to 0.2 inches. I'm going to leave that as is. And we have our top plane, which is set to our Z0. That's going to be 0 inches. Again, that's perfect. We're going to leave that as is. And then we're going to look at our bottom height, which is from selected contours. Now, you may remember when we measured our stock material, it wasn't exactly ½ inch, while our model is exactly ½ inch. So what we're going to want to do is we're going to want to change this from model top, and we're going to want to go negative 0.47, which is how thick our material is. And then to ensure we cut through our material, we're going to want to add a little bit. So we're going to add 20,000 of an inch, so we're going to go negative 0.49. This is going to ensure that we cut through our part while not cutting too much into our spoil board on our machine, which is the sacrificial wood that you're going to bolt your part to make sure you can cut through it. And now it's going to show right here our bottom is negative 0.49 from the top, which means our machine tool will be cutting 0.49 inches below the 0 surface, which is just slightly above the thickness of our part, and we're going to be good to go. You do always want to make sure you take a real measurement and double check this number, as it is critical to make sure you cut for your part. At the same time, you don't want to cut too deep, damaging our machine and cutters. After we do that, we're going to go to the next tab, which is going to set our passes. And the only thing we're going to want to really adjust here is the multiple depths. We're going to click that, and we're going to set the maximum roughing step down to 0.25 inches. This means the tool will be only cutting 0.25 inches deep at a time so that we don't overload the tool or overload the machine. In our testing, we find that 1/4 inch is about what you want to use for this number. I'm going to actually leave all these other variables as is, as I know the defaults will work. You're going to want to take a close look at your screen and my screen and make sure we're on the same page. There are other options like finish passes you can enable in these 2D contour toolpaths, which again, as I said earlier, might be useful when you're cutting metal or harder plastics, but for wood, I don't find them necessary, so we're just going to leave them as is. Again, we want to make sure stock to leave is unchecked because I don't want to leave any stock. And then we're going to be able to go on to our next tab, multi-axis, 3-axis, that's perfectly fine. Then linking, which we're going to then enable our ramp. This will ramp into our part, and we're going to leave it as the default 2 degree, as that's going to be a very nice gentle ramp. And then the lead in and lead out defaults will work for this as well. Now, the more experienced you get, the more you can push the machines in these settings. These are all fairly conservative, and more experienced users might be able to get a little more speed and optimization out of these toolpaths. However, sometimes it is, in my opinion, not worth the effort to save a minute or two when you're potentially risking the machine or the tool breaking. So we're going to run really conservatively for this part. We're going to hit OK, and now Fusion will generate our 2D contour. As you can see, the tool will now be contouring around the outside of our part. We got our red lines for our ramps, we got our blue lines for our cutting, and we have our yellow lines for our retracts and lead-ins and lead-outs. Now that all looks really good. So once we're happy with that, we can click the setup, and then we're going to actually click the simulate with machine option here in the actions tab, and that will pull up this simulation view where we can click play down here, and we'll simulate our entire operation. Now when we're watching this, we want to make sure that we're watching for where the tool is going, that the tool isn't going anywhere we don't want to, or causing any gouges in our parts. And then over here in the statistics tab, you can click that, and it will give you an estimated runtime of how long this is going to take. According to this, it's going to take 3 minutes and 33 seconds, so that's going to be fairly quick. You always want to do this to make sure that your tool is cutting what you want to cut, and you also know how long it's going to take, so you can budget your time in the makerspace accordingly. Now this is cutting. Let me tell you about today's sponsor. Hint, we don't have one. After that's all done, we're going to hit exit simulation, and now we're going to be able to post-process our G-code. Post-processing is the process of exporting the G-code from the CAM software that we're going to put on a USB drive and take it over to a machine. It is basically the same thing as what is known as slicing in the 3D printing world. So to do so, we're going to right-click our setup. We're going to hit post-process. Now, what this will do is it will post-process all of the operations in our setup. So it's going to combine these two operations into one file. Personally, when I'm using different tools on a router, I'll often post-process operations in batches. So I'll have one file for every tool I need to run so I know to do my tool changes. And that's a popular way of doing it. You can also post-process every operation as an individual file if you want to run them sequentially. In case something goes wrong, you can then go back and change something. But because this is only one tool and a relatively simple part, I'm just going to post-process everything as one file. In the post, you're going to want to select the Carbide 3D post processor. Now, this is what we're going to use for our Shapeoko CNC routers. Every CNC manufacturer does their post-processing and G-coding a little different, so you want to make sure you use the right one for your machine. Now, if you don't have this option in your computer yet, you're going to want to go choose from library, select the Carbide 3D one, and then copy it to your local library, and then you'll have it as an option. We're going to name this part something we can read and find again, so call this test block. And then I like to put in the tool I'm using inside the file name. So I'm going to do -6mm end mill. And this will know that when I'm loading the file, I can also have a visual remember what tool I need. And we're going to go ahead and save it to your flash drive. I'm just going to put it on my desktop personally for now. And hit post. Once the code is post-processed, you're going to be able to take the flash drive and take it over to the machine and then start setting up the machine and running your program. Again, if you have any questions, feel free to reach out to a staff member. We'll do our best to help you out with this, and hopefully you've learned something today.